Hi, I'm John Stevens, the CTO and a co-founder of Veridise. Today, I'm going to show you Veridise's real-time smart contract auditing service. Let's get started. Here, you can see an interface where someone can upload their contracts. To audit the contracts in this editor, simply click the Analyze button. This sends the contracts to a Veridise server that runs them through our automated auditing toolchain. This toolchain has a few unique capabilities. First, our tools are designed to be blockchain agnostic. This means that Veridise can quickly support new blockchain architectures and languages. Second, this process is entirely automated. That means our clients can get feedback about their smart contracts almost immediately. At the same time, our tools are undergoing constant improvement to ensure that they capture properties that our clients care about. You can see that we have popped up a PDF report. Let's skip over the boilerplate information and see what was discovered. We can see in this summary that 5 potential issues were discovered using Vanguard, Veridise's tool for detecting common vulnerabilities. These vulnerabilities are ranked by the possible severity of the issues based off of our experience and community consensus. We can see that there are 4 high severity problems and 1 medium severity problem. If we continue to scroll, we can find more detailed information about the vulnerabilities detected. The first vulnerability detected is a possible reentrancy vulnerability. The report identifies the withdraw function might be vulnerable to a possible reentrancy attack and gives a detailed description about these attacks. Let's look back at the code and see what it found. If we look at the identified function, the report says that the balance contract variable was modified after an external call. We can see that this is indeed the case, and therefore this function is vulnerable to a reentrancy attack, since upon reentrancy, balance will hold a stale value. Next, we can see that we identified a possible flash loan attack. The report states that a contract is potentially vulnerable to a flash loan attack if the price of an asset is dependent upon some entity's token balance. We can look back at the code to see if this is the case. We can see here that Uniswap pair's token balance is used in the price computation. That means by using a flash loan, an attacker can inflate the number of tokens owned by Uniswap pair and therefore cause the price of the asset to shrink. That means that borrower is indeed vulnerable to a flash loan attack. The third vulnerability that we find is an unprotected self-destruct. A self-destruct will delete a contract and send any remaining balance to some designated beneficiary. As stated in the audit, an unprotected self-destruct can send funds to an undesired address or prematurely delete a contract, creating an effective denial of service. We can see by looking at the identified function that the developer didn't identify the beneficiary of the crowd sale and likely intended the close function to be only called by the beneficiary. Without such a check, anyone could close the crowd sale and take all of the money raised. The fourth vulnerability discovered was an uninitialized address. In Solidity, an address is automatically initialized to the 0 address. If an asset is transferred here, it is therefore locked since this address is inaccessible. If we look at the contract, we can see that the beneficiary contract variable is shadowed by a variable in the constructor. Thus, the assignment of the constructor's first line does not do anything, and the beneficiary variable goes unassigned. This will result in funds later being lost when the close function is called, since it will cause the funds to be transferred to the 0 address. The final identified vulnerability is the use of message value in a loop. Using message value in a loop is a common anti-pattern because it corresponds to the amount of money that a single address, message sender, sent to the contract. It is therefore uncommon for message value to be required in a loop since it typically only affects a single individual. If we look at the identified function, we can see that this may be safe since it appears that the contract intends to split a payment between multiple recipients. However, we can see here that this is indeed a bug since each recipient is sent message value. That concludes the report in this video as well. We hope you enjoyed this look at Veridise's real-time auditing process and encourage you to view some of our other videos, such as our video on how we synthesize attack programs for DeFi applications.